and we can say over there. Bond energy, basically bond energy. Bond energy is the amount of energy required to break the bonds of 1 mole of a molecule, the bonds of 1 mole of a molecule into its proper elements over there is called bond energy. And this bond energy, I will say here that it will be measured in kilojoules per mole over there. This is the unit for it. And we can say that the atoms here should be in gaseous state for the molecules formation. The molecules should be in gaseous state over there. And when we are going to break towards the pi bond, that will be a weaker bond than sigma bond over there. As we are talking in bond energy, then I am saying here that double bond is having both one sigma bond and one pi bond. And this pi bond is weaker as compared to your one sigma bond over there, which is present in double covalent bonds over there. Bond energy, we will say here, for example, I am taking an ionic bond. I am taking a covalent bond like CO2 in the form of double or CCl4 like that. All are the covalent bonds or ionic bonds are being broken down in their gaseous atoms over there. We can say they will be broken down by providing energy to the molecule over there by endothermic process over there. Means bond breaking is endothermic process or endothermic reaction over there, in which we will have to provide the energy and provide energy over there. In that case, I will say whenever we are going to take the value of bond energy to break the bond over there, it will be being taken from the outside towards the system. So it will be having always the positive value over there because it will be given to the system to break the bonds into their singular gaseous atoms over there. After that, there is the second one that is called bond length over there. Bond length. Bond length is basically, we can say, is the distance in, is the intermolecular distance, we can say, is the, it is, it is the intermolecular distance, intermolecular distance between two atoms in covalent bond. It is the intermolecular distance between uh, in covalent bond over there. And we can say, let's suppose I am taking two bonds like hydrogen here, and I am taking also another hydrogen atom over there. Then when they are equally distributed, then the distance between their centers is called bond length over there. So if I am taking the bonds of different nature, like I am taking some atom with larger radii produce molecules with greater bond length with their valence electrons as they move away from the nucleus over there, like that. For example, I am saying that I am taking chlorine here, and I am making a chlorine which is having first shell with the 2 electrons and the next shell with the 8 electrons, and the third shell with the 7 electrons. 1, 2, 3, 4, 5, 6, and 1 7 electron, and one hydrogen is going to attach now here, then the bond length between the center of the chlorine atom to the center of hydrogen atom over there will be being taken as the larger distance. And I am telling about this, atoms with larger radii like chlorine over there will be providing here the greater bond length because it is having more shells over there. And these shells are creating because the valence electrons are further away from the nucleus in case of chlorine atom over there. And on the other end, if I say a shorter bond is present, indicates that bond is stronger due to electrostatic forces of attraction. If I take Na and Cl negative, then even though sodium and chlorine, sodium is having only two shells over there, and chlorine is having again the three shells over there. But due to the presence of strongest electrostatic force of attraction on both of these ions, on the cation of sodium and anion of chlorine over there, I will say they are tightly being packed and their bond length will be shorter over there, being taken from Na to Cl in that case. Let's suppose I say in case of NaCl, then bond length is not being considered as like in case of covalent over there because the sodium and chlorine will be tightly packed due to their ionic bond over there. After that, in case of covalent bonds and intermolecular forces over there, we will say what to move next for us. Wait a second. Bond energy, then bond length. Okay, after bond length, relationship with the reactivity of a molecule with bond energy and bond length over there. Okay. This reactivity, basically, he is saying that how they are being linked over there. Both of these points will be taking into account that although bond strength increases with the increase in shaded pair, double and triple covalent bond. For example, carbon to carbon single bond is present. On the other end, carbon to carbon double bond, carbon to carbon triple covalent bond is present. Then in that case, the bond strength is increasing by the way, but when we are looking towards single bond sigma, more stable and less reactive because the electrons are concentrated in between the bonded atoms. When we studied about sigma bond, we said that it is being formed due to head-to-head overlap. Like sigma bond is formed due to head-to-head overlap, head-to-head overlap, even though that is the other one in which the pi bond is present over there, they are less stable and currently available for very fast reaction over there. So when we say that the bond strength is even though increasing between because of the double and triple covalent bond, but single bond is more stable and less reactive because electrons are being taken in the form of bonded atoms by head-to-head overlap, whereas in the pi electrons are easily attacked by electrophile over there. That's why alkynes or alkenes are more reactive than alkanes over there. In organic chemistry, we will also study about their double and triple covalent bond nature over there, in which we will study that pi bond is available for very fast addition reactions by those compounds over there. After that, if I say about bond length, as the bond length increases, it becomes weaker and hence more reactive. So we can say here, if the number of bonds are increasing, reactivity is increasing by the double or triple covalent bond. And if the bond length is increasing, then the main atom is going to be easily attacked by the other electrophilic or nucleophilic attackers over there. And they are showing less attraction from their centers over there. And they are easily going towards nucleophilic substitution reaction of halogenoalkanes or reaction of hydrogen halide with alcohols over there. If we take these examples over there, like substitution reaction, if I simply say here CH4 is a methane, I am reacting it with chlorine. One by one, it is going to show CH3Cl is formed. Then again, I am adding chlorine, it is going CH2Cl2. If I am going again to add chlorine more, then it is going CHCl3, and in last case CCl4, carbon tetrachloride I am getting over there. Then in all of these cases, we can easily observe that they are being attacked due to carbon is having two shells, hydrogen is having one shell. So bond length is increased, and our hydrogen can be easily replaced by the chlorine molecule over there, and giving some HCl as a product with all of them over there. And such is the example of substitution reaction. And in case of reaction of hydrogen halide, means like HCl is reacting with alcohol, giving the salt and water over there, means when acid and base reacts with each other, they give salt and water. Salt plus water over there. They are also going to show the, we can say, substitution type reactions over there. They are, both ions are being substituted and getting more towards the reactivity over there. After that, he is saying over here the relationship between reactivity of molecule with bond polarity. Polar molecules are more reactive than non-polar molecules. We have studied about polar and non-polar molecules over there, in which we said that polar molecules are those molecules which have electronegativity difference over there, and non-polar, we said they have polarity difference very less, like 1.7 is the standard given by the Pauling scale over there for electronegativity. And when they are polar molecules, they are more reactive. And when they are non-polar, it means they have low electronegativity difference or approximately equal to zero, like that. Then they are going to show non-polar behavior of molecules, like CH4 in the form of examples. We can say it is non-polar molecule. So we can say here HCl is more reactive than chlorine, because HCl is having the electronegativity difference. In case of chlorine, when I am taking Cl2 over there, then electronegativity difference is zero over there. When if I am taking HCl, then it is 3.5 and 2.5, and then the difference is 1 point something over there is available. CO is more reactive than N2. And he is saying reaction with iron of hemoglobin, like if you are studying biology, then I'm so sure you will be confirmed over there that when there is not sufficient oxygen available, then carbon dioxide is producing, and with the passage of time, carbon mono is producing, which is going to react with hemoglobin, and suffocation is being felt by the patient over there. After that, CH3Cl is more reactive than CCl4. It means it is having CH3Cl is having the electronegativity difference, which is going to be shown over there at according to bond polarity, and partial positive and partial negative ions can be formed over there. So this was your bond length and bond energy and bond polarity was being added over there. And I'm saying here the next one is bond polarity. Bond polarity comes because of electronegativity difference, and it is responsible to make partial positive or partial negative ion for polar molecules, and polar molecules also more reactive, and they dissolve in polar solvent like water. On the other end, if I take the example of non-polar molecules over there, then I say those will be taken over there. Electron distribution will be permanently symmetrical. In that case, then we can say that they have equal bonds over there. Then we will say non-polar are going to show very slow rate of reaction. On the other end, I will also say that non-polar molecules are responsible for dissolving in non-polar solvents like petrol.
No,
Yes, beta, you have any question there?
no.
Okay. So this is related to bond polarity. We have discussed till now bond energy, bond length, and bond polarity over there. If I compare all of these sections, in the form of polar and non-polar like that. Then the structure of ionic, structure of covalent, which is in the form of, we can say, polar covalent. And then I'm going towards non-polar covalent, non-polar. If I scale all of them, then I will say ionic are those compounds which are having the electronegativity difference greater than 1.7. Like I take NaCl, then I will say Na and Cl. Cl is Na is having 0.9. On the other end, Cl is having 3.0, then it is 2.1, which is greater than 1.7. It is showing that it is ionic compound. And if electronegativity difference is less than 1.7 over there, then I am saying here, like approximately, it should be 1 or greater than till 1.7 over there. Then I will say I'm taking, for example, I'm taking here carbon monoxide over there. In that case, I say the oxygen is having 3.5 as electronegativity, minus carbon is having 2.5 again, and it will be taken as 1 as electronegativity difference, which is showing a reasonable value from as compared to 0.5 or 0.4 over there. Then I will say it is polar covalent compound over there. In case of non-polar, I will say there that, for example, carbon to hydrogen, you are taking only carbon hydrogen bond to show its polarity. Then we will say, now I'm going towards non-polar covalent. And if I take carbon, we know that is 2.5, and in hydrogen is 2.1, then it is going only 0.4, which is approximately very much near to zero, are showing the non-polar covalent bond in that case over there. On the other end, if I go towards the polarity in molecules, now I am going towards intermolecular forces over there. If I say that polarity in molecules to be taken into account, polarity in molecules, like we are getting ammonium ion, we are getting carbonate ion, we are getting sulfate ion, polarity in molecules over there. In that case, means I will say that the overall dipole molecule depends on the shape and electron distribution over there. For example, let's suppose I take H2SO4 over there. Then I can say that when I dissolve it into water, I'm getting -2 on it and +1 for hydrogen. For 2 hydrogen, it will be 2H plus ion and SO4 -2. Then in that case, I will say here, then there these are the moments which are being produced in the form of dipole moments over there, depending on the relative angles between their bonds, and the individual dipoles can either reinforce or cancel each other. For example, I simply say here, sulfate ion with 4 oxygens are being attached over there in the form of O4, SO4, with -2 over there as its ion. And if I am taking some other hydrogen ion to attach over there, and if they are going to cancel out its effect, then they are going to get hydrogen sulfate over there. But if I take only the sulfate, only species over there, then this species is going to become an ion, molecular ion in case of water, like that when it is dissolved and diluted sulfuric acid is taken out. If the effect is not cancelled out, then I will say it will be remaining with its -2 charge. If hydrogen is coming, for example, one hydrogen is coming towards SO4, and it is giving me hydrogen sulfite ion over there, it is still needing one more ion over there. Then this is the net charge for that polarity responsible in molecules over there. After that, I will say what is, I use the word dipole moment while explaining it. Dipole moment. In physics, you have studied in IGCSE what is moment. Moment was turning effect of force. Turning effect of force over there. And you use the formula for tau is equal to R cross F over there. Here I will say The same case I will use for explaining the dipole moment over there. And I will say it will be like you have studied about vector sum of the quantities, because your moment was a vector quantity over there. So dipole moment is a vector sum of dipole moments, vector sum of dipole moments, vector sum of dipole moments of all bonds which are exerting some forces from their central molecule. And if molecule dipole moment is not zero, if vector sum of all the moments is not equal to zero, then we will say the molecule is polar over there. If it's, for example, I'm taking an example over here like carbon with oxygen over there, carbon with oxygen. What I'm have saying that the bond angle is 180 degree, and the moment is going to having its value equal to zero. Tie is equal to zero. Then in this case, I will say there is no polarity is available over there. But if I go towards vector sum for having its molecular like CH2Cl2. I am taking this molecule over there. Then I am saying carbon is present over here, having two hydrogen over there, and I am saying having two chlorine also attached with it. Then we know that due to electronegativity difference, there will be a moment that will be produced due to its molecular structure as a net moment in this direction, which I have shown over there. Then I will say that the carbon atom is going to show partial positive and this chlorine is going to show partial negative. And your this chlorine, the other chlorine is staying neutral over there. Then there will be a dipole moment that the molecule will be attracted towards this direction and will be rotating towards this direction over there. So that is going to give us a dipole moment concept of physics here in explaining molecular structure. After that, bond polarity also influences, we can say, chemical reactivity over there. Bond polarity influences the chemical reactivity, in which I will say that many chemical reactions begin when a reagent attacks. Like, for example, I am taking here this carbon dioxide like that. This is overall neutral. What is happening? That its reactivity can start when some electrically charged molecule is coming towards it, and its bond polarity is disturbed, and its pi bond is going to be broken down over there to show some reactivity over there. Then it can easily be taken. But here, when I have given this example, for example, this example, which is having some polarity over there, the carbon dioxide needs some polar ion. On the other end, this molecule, which is already having its bond polarity over there in the form of bond dipole moment over there, then it can easily be attackable, showing it's more reactive as compared to carbon dioxide molecule over there. I can also take the example of N2, which is having the bond polarity as zero, is mostly unreactive, very slow. Reaction is being given by this molecule. But this one, which is having some polarities over there, is much more attracted and showing the more influencing towards its reactivity over there. If we go towards intermolecular forces, I will say here, intermolecular forces are of basic types, in which I will say instantaneous dipole-induced dipole forces. Instantaneous dipole-induced dipole forces. IDID, instantaneous dipole-induced dipole forces. These forces are means I will say these are attractive Intermolecular forces caused by temporary instantaneous dipoles in molecules means, for example, you are going to add non-polar molecule into polar molecule. What will happen? Polar is already having positive ion and negative ion over there. When you intermix them non-polar with polar molecule, what will happen? Like alcohol and water or something, then what will happen? That polar are going to induce, means that is induced dipole, instantaneous dipole, induced dipole. In non-polar, the poles will be induced and both are going to show intermolecular forces in the form of attraction over there. This is the first type. Second type is related to permanent permanent dipole permanent dipole forces. Dipole forces over there. What I said? Permanent dipole forces over there. Permanent dipole forces over there. Then what we'll say, for example, we are taking attractive intermolecular forces caused by permanent dipoles in molecules, like polar molecules. You are going to dissolve HCl into water, H2O. You are observing HCl is having positive ion, Cl is having negative ion. On the other end, water is having H plus, water is having OH negative. So both have permanent dipole, and they are going to show attraction and going to dissolve each other over there. And at the last, there is hydrogen bonding. That is most important. That is number 3. That is hydrogen bonding. Hydrogen bonding is the intermolecular force which is being reinforced or observed due to high electronegative atom. For example, I'm taking water over here and I'm getting oxygen and hydrogen. Oxygen is more electronegative, so I say it is having partial negative, it is having partial positive, it is having partial positive. What will happen? I'm taking another water molecule with the oxygen. What will happen? Its hydrogen is going to be shown its attraction little bit towards oxygen. Or I am taking one more molecule of hydrogen, water over there. What is happening? Its hydrogen is here, its hydrogen is here, its hydrogen is trying to make the weak intermolecular forces in the form of hydrogen bonding with the other oxygen atom over there due to the presence of partial positive and partial negative ions charge over there. So such simple discrete molecules and giant molecules can show the phenomenon of hydrogen bonding. As I have taken water, I can take HF because due to high electronegativity of fluorine, it is having partial negative and it is having partial positive. Even in the complete as a liquid over there, HF, then this F is also going to show its attraction towards partial positive of next hydrogen fluoride molecule over there with partial negative, and this hydrogen is going to be shown as an intermolecule. I am giving with a dotted line towards the notation of I can say hydrogen bonding shown over there. So I am taking here fluorine again with the partial negative and hydrogen here with the partial positive. And their bonds between atoms I'm showing with the dense line, thick line over there, and dotted line I am using here with the hydrogen bonding notation over there. And if I say instantaneous dipole-induced dipole forces as was given in the first explanation over there, then I will say a non-polar molecule may be temporary dipole from randomly dipole force randomly over there. And for example, I say here, I am taking a neutral non-polar molecule. This is a non-polar molecule. It is surrounded by two more molecules which are polar over there. For example, this is having partial negative at this end, and this is having also partial negative at this end. Then what will happen? That the molecule will be inducing positive ion on this side. This is having positive, this is having negative. This is having positive. Then this molecule, which was originally neutral, which was not having any charge, will get randomly a force to induce dipoles at this molecule, which will having partial negative and partial positive on its molecule. When these molecules are removed, then it will come back to its original state of neutral state over there. So always remember, whenever such a thing is going to happen, then there will be electronegativity difference, there will be electron distribution difference over there to be taken into account. And in case of dipole forces and hydrogen bonding, we will say the most strongest intermolecular force is hydrogen bonding, due to which I can say the boiling point of water, if I compare it with the alcohol, is higher as compared to alcohol due to this hydrogen bonding. And if I say water gets more characteristics, then we can say water is having the characteristic when water is freezed in the form of solid ice, it starts to float over there. Then it is also responsible to show that hydrogen bonding is available over there, which is showing that its volume is increased. And according to the physics formula of density is equal to mass over volume, when volume is increased due to this hydrogen bonding, they are going to settle down, volume is increased, density will decrease, and ice will start to float over the surface of liquid water over there. At 0 degree centigrade, ice is formed, but that is lighter. In all other liquids, when they freeze, they settle down. They are not to start freeze from the top over there. Only water can do such phenomenons over there. This is because of hydrogen bonding over there. So I will say here, these were the intermolecular forces, bond energies, bond lengths, bond polarity, and dipole moments to be taken into account. If we look towards our topic over there, then I will say here, he has also tried to explain the metallic bond. Metallic bond रह गया है. Metallic bond. Okay. Intermolecular forces. Hydrogen bonding is the most strongest bond over there. Attractive force, permanent dipole, induced dipole is there. After that, molecular size, chain structure, permanent dipole forces, dipole molecules to be taken into account. After that, hydrogen bonding. And that hydrogen bonding in case of water molecule, I have given you in the form of example. Here he has also mentioned that the 100 degree centigrade temperature is very high, like the same compound like H2S is in gaseous state, but H2O at room temperature is liquid and having very high boiling point, while H2S is having minus 86 degrees centigrade, means it exists as hydrogen sulfide. And it is not showing any type of hydrogen bonding over there. Water is having, this is the hydrogen bonding bond over there. And ethanol molecule he has shown, ammonia molecule is making hydrogen bonding. So this was your today lecture. And in the next class, I will also try to do metallic bond and these past paper questions over there. All right.
Okay. Okay.
Okay. Thank you so much for today. And please kindly revise the whole chapter, because tomorrow you will not have class. And on Sunday you will have class. We will do a practice of whole chapter in the form of past paper questions. Kindly do your practice.
Okay.
Thank you so much for today. Allah Hafiz.
Thank you. Love this.
Allah Hafiz, mera beta. Allah Hafiz.